This problem's an interesting one. So as we go through it, make sure you pay attention to the intricacies and all. There's a lot of little details to it. All right, so what we're seeing here is we are given a function that is a relationship of dx dt. So let's pay attention to the units on that. All right, so now we are going to say that, and you're going to find that in the problem here. We're going to say right here. Well, notice that it is calculators per week. This function is calculators per week. So the dx represents change in calculators. Maybe I'll use a d, I'll just use the word change in calculators. And therefore the dt is change in weeks or time, right? But it's specifically weeks for this problem, change in weeks. Okay. Now, so if we imagine what this function graphed would look like, which this isn't necessary, just trying to build the picture. If we were to imagine this, this would be, what are we putting into this function? Well, t is the input variable, right? So therefore, again, this would be weeks, because we already said dt is change in weeks, so therefore t would just be weeks. And then the output would be the dx dt, right? We're getting out dx dt, which would therefore be calculators per week. Okay, so if you can imagine that. Now, we want to ask ourselves, what would the integration, whatever that function might look like, what would the integration look like? Well, the integration would be the area under the curve, right? Which is width times height. And so therefore that'd be the units of weeks times calculators per week. Calculators per week times weeks. So therefore the weeks would divide, leaving us with the units of calculators. So what this function would do is if we integrated this, it would give us the number of calculators, right? This area, width times height, this area would represent the number of calculators. Now, is it the total number of calculators? No, it's the calculators that were made those weeks. Okay, so let's go back and see, now putting that idea together with the problem, let's see if we can make some sense of this. Let's see, Alabama Instruments Company, Okay, so production approaches 1,400 per week as time goes on. That's what this formula is representing. But the initial production is lower because the workers are unfamiliar with new techniques. This makes sense. That's logical. Production always ramps up. Here we go. Here's the question. Find the number of calculators produced from the beginning of the second week to the end of the third week. Okay. And they're telling us assume t equals 1 represents the beginning of the first week. All right, that's going to be key. So if they're asking us to find the number of calculators, well, hey, we just said that would be the integration. All right, so we're going to integrate this function because that will give us the number of calculators. So we're going to integrate 4,100 minus 4,100 times 190 over t plus 15 squared dt. There we go. All right, but when do we start and when do we end? Well, and this is where one of those major details pops in here, because they said assume t equals 1 represents the beginning of the first week. So they want to know from the beginning of the second week. So we're going to start at week 2. But if we put to the end of the third week, so if I put a 3 here, that wouldn't mean the end of the third week. That would mean the beginning of the third week. So the beginning of the third week, the end of the third week would be the same thing as the beginning of the fourth week, right? Before we actually get to it. So we're going to integrate from 2 to 4. That's one of the main parts to this problem. Now, once we have that, we just want to keep in mind what this represents, right? Do they want to know the total number of calculators or just the number of calculators produced in this period of time? And we can see here, let me clean this off. What we can see here, when we go back to this area right in here, they want just the number of calculators produced, which is perfect. This is the net change. This is what this function will give us. So we integrate and we'll be ready to go. So we're going to go ahead and break this up into 2. Well, we can kind of leave it. Just remember we have 2 separate problems because we have the subtraction in the middle, right? So we're going to think of this as one antiderivative and this is a second antiderivative, right? Okay, now for the first one, the antiderivative of 4,100 would just be 4,100 t. evaluated from 2 to 4. Actually, I'm going to do this in two problems just to kind of help us keep track of this antiderivative. So then we're going to say, I'm going to do this one in just a second here. T plus 15 squared dt. Okay, going from 2 to 4. All right, now this first one was easy. This is just the power rule. This one's gonna be a little more interesting. So let's clean it up, make it as easy as possible. I'm gonna take all of my constants. I'm gonna take that was supposed to be a highlighter. Let's try that again. I'm gonna take this 4100. I'm gonna take this 190 because those are constant multipliers, and I'm gonna move them both to the outside and multiply them. So to do that, I'm gonna need a little help. And let's get that calculator back up. There we go, clear. All right, so 4100 or 4100 times 190 would be a big number. All right, so let's not ever lose anything as we go. We're gonna leave this written like that. Minus 779,000, 779,000. But now on the inside, I'm just left with what I'm still integrating is 1 over t plus 15 squared dt. All right. And that should be it for the calculator for now. Okay, now what? Well, let's see. We have a little chain rule. So we know that we can use U-substitution at this point. So I'm going to let U be 2 plus 15. So therefore, du would be dt, okay? And if we have that, that would result in, and we'll see, we actually didn't need to use U-substitution. We could have used a little bit of guess and check and just gotten through it, because what we're going to see here is 4100 t evaluated from 2 to 4 minus 779,000 from 2 to 4, 1 over u squared du, because dt is the same thing as du, right? And that whole inside, just the t minus 15, t minus 15. So if your teacher hasn't taught you U-sub yet, if maybe this is appearing somewhere before, don't worry, you'll see it. Just a little bit of guess and check, we'll get the same answer, just using a tiny bit of logic. Okay, so don't panic if you don't recognize what I'm doing. Okay. All right, so now what is the antiderivative of u squared if it's in the denominator? Well, we'll do a little bit of rewrite. Let's rewrite this as u to the negative 2 du. So what is the antiderivative of u to the negative 2? There's a lot of rewriting, I know, but it's to make sure we don't miss or lose anything along the way. All right, so what is the antiderivative of u to the negative 2? Well, that's a power rule, so that'd be u to the negative 1 divided by negative 1, but we could simplify that and just rewrite that as negative u evaluated from 2 to 4. And if we want to, on this next step, I'm going to take that negative to the outside and make that a plus, okay? So that's going to give us 4100 t from 2 to 4 plus 779,000. And then I'm going to rewrite this as 1 over u evaluated from 2 to 4. And actually, I should be really careful. I'm going to make sure, I'm going to go back and change something. I'm going to make sure I just remember that this is t equals 4 and t equals 2. T equals 4. This isn't a u value. This is a t, right? These were our times, just so I don't accidentally sub them in for u. Okay, now let's go back and put our problem back to where we started. Okay, plus 779,000. So what was u? Well, I go back and say, well, u was the same thing as t plus 15. Okay, all right. So therefore, t plus 15 evaluated from 2 to 4. Okay, now I'm done. And so now, well, I'm not quite done, but I'm close. But the thing I want to point out, for those of you who may have seen this before you use the U-substitution, we can get away with just thinking of this as we don't really have a chain rule, because think about if we were doing derivatives. What is the derivative of the inside t plus 15? Well, that would just be 1. So therefore, there is no real chain rule necessary, only because of luck, right? Because it was written that way, where the inside, the derivative of the inside doesn't matter. So same thing for the antiderivative. going backwards with it, the chain rule doesn't matter. So it would just be, we could think of this as just the same thing as just if I had 1 over t plus 15 to the second, well, as a little rewrite, we could think of that as t plus 15 to the negative 2. Oh, I should have my dt there. And then what is the antiderivative of that? Well, we would say, well, we'd add 1 to our exponents, so that'd be t plus 15 to the negative 1 divided by negative 1. And you'll see we'll get right back to what we had, right? By luck, because the chain rule was 1, right? But that's okay. That's okay. So there we go. All right, now we're going to sub in our values. So this is going to be 4100 times 4 minus 4100 times 2 plus 779,000 times 1 over, I'm going to sub in my 4 now, 4 plus 15 minus 1 over 2 plus 15. And now this is where it's going to get really, really fun. We're going to use a calculator. There we go. This is difficult to type in, so please make sure you're not just blindly copying, because when you're typing this on the screen, sometimes things don't go well and I miss a number or it doesn't register. All right, so this first one, this first part here, this would be 12200. Okay, plus, now over here, this is where it's going to get really fun, 779. I'm just going to do the fractions. So I'm going to do, what is this, 1 over 19? 1 over 19 minus 1 over 17. And let's turn that into a fraction. So this would be negative 2 over 323. And let's take that number and multiply it by 779,000. There we go. So we have 12200 minus 4823.529412. That really doesn't matter. And if we wanted to, we could turn that into a fraction if we wanted to keep it exact. No, we can't. Calculator can't handle it. But it really doesn't matter because the problem told us, I believe it, to, yes, round to the nearest whole calculator. We're talking about producing calculators. So these decimals are a little, unnecessary if you just stop and think about what do they mean. So what we're just going to do is say this is 12200 plus our previous answer. So that means we are going to end with 7376. And if we're going to round down because it's 0.4. So it's 7,376 calculators. There we go. All right. So what does that mean? It doesn't mean that we have a total of 7,376 calculators, right? Because this is net change. This is the production between the beginning of the second week and the end of the third week, right? Beginning of 2, end of third, which would be the beginning of 4. Back to the very beginning of second week, end of the third week. So therefore, how many calculators do we produce during those 2 weeks? 7,376, right? I hope this helps.